Welcome to part 6 of our live training process here with our forced induction K-Series G4x plug and play example. Now, in the last tutorial, we finished up our wide open throttle tuning for our high cam operation. So at this point, everything has been dialed in. This tutorial, we're going to be taking a look at doing the cold start, making sure the engine can crank and fire and run at an appropriate air fuel as it's coming up to operating temperature. So we're going to go through that process. We're going to take a look at setting up a launch control as well as looking at our acceleration enrichment. These are the last pieces of the puzzle before we move on to our last tutorial, taking a look at our flex fuel calibration process. We have a lot to cover. Let's jump in so we can check this out. Welcome back to our live training session here with our supercharged K-swapped NSX running on a plug-and-play linked G4x system. Now, the last few tutorials we've looked at the calibration process from start to finish, looking at the idle control, part throttle, and wide open throttle tuning. That was all done on a warm engine. Now we're ready to take a look here at day 2, where we let the engine sit overnight. We're going to fire it off and evaluate our cranking fuel, our post-start fuel, and our warm-up enrichment fuel. Now we're going to go over what those mean here in just a few minutes, but I first want to talk about what happens on a cold engine and why our fuel demands and the spark timing demands will be different. We're going to find on a cold engine we have two different factors we have to overcome. One is going to be the oil viscosity being thicker. There's more frictional drag on the engine, and as a result, we're going to find that the engine's torque production is going to be a little bit lower when compared to when the engine is warm, and the viscosity is going to be thinned out on the oil, so there's less frictional drag and there'll be more available torque at the same airflow coming into the engine and same fuel and spark timing compared to a cold engine. So we're going to find when we fire off an engine, it's going to naturally want to idle a little lower. Now, typically what we do is we use the idle air control, or we use drive-by-wire, whatever type of idle control we're dealing with, that allows us to enter in some more airflow to the engine to offset the lost torque. Bringing more airflow allows more torque production out of the engine. We can offset that frictional drag on the engine with the engine oil, the viscosity being a factor, so we can get around that. Now on this particular engine, we've deleted the idle control motor. We don't have drive-by-wire, so we'll see how it's going to go. We do have some spark timing adder in our spark timing ECT compensation table that adds additional spark timing on a cold start to try to get back some of the lost torque from specifically this frictional drag. We'll see how that goes when we try to get the engine to fire off here in a few minutes. Now, the other factor we have to account for and deal with is a wall wetting factor. Now, wall wetting is going to be there whether the engine's cold or warm, but on a cold engine, it's especially going to be a consideration that we have to take a look at and we have to get around. Now, with the wall wetting factor, it's when the fuel sticks to the intake track and to the intake valve. It doesn't want to get into the engine as efficiently as possible. That's largely part from the poor atomization of the petrol fuel spraying out of the fuel injector when the engine's cold specifically. Once we have warmer air temperatures in the intake manifold and the cylinder heads, we'll find that the fuel wants to atomize much better and it gets into the engine more efficiently. So when we're firing it off an engine, we're going to find that this wall wetting factor is going to have kind of a couple different impacts on the engine. One, it is going to reduce down the torque production of the engine a little bit, and it's going to require us to add additional fuel on a cold start because the fuel isn't going to get into the engine as it would efficiently when the engine is warm and the atomization out of the injector is proper. So we'll find what we have in place to be able to compensate for this is a post-start and a warm-up enrichment table. The post-start's applied for the first 5 to maybe 30 seconds after the engine's fired off to provide stable combustion. And then it transitions right into the warm-up enrichment, where it's going to have more of a long-term percentage modifier adder against the base pulse width calculated from our main VE table. That's our airflow modeling. So whatever that figures out for a pulse width, it'll multiply it by a certain percentage based on the engine coolant temperature that we're at. And we'll find we dissipate it away and go back to zero warm-up enrichment once we get up to what we consider to be operating temperature. Usually about 140, 160 degrees is normal operating temperature. At that point, the engine will run efficiently, and the wall wetting factor in terms of the poor atomization and having a little bit leaner mixture as a result of that poor atomization will start to dissipate and go away. And then we can focus right back on to being on the main VE fuel table with what we've already calibrated in the last few tutorials. We were always on a warm engine. We're anywhere from 160 to about 200 degrees Fahrenheit in the range we were operating it in. So we were always in that normal range. That's what's calibrated in terms of the fuel and airflow modeling. Now we're adding on to that. So let's dig in here real quick. If we jump here into our fuel trim, we're going to find that we have our cranking enriched, we have our prime pulse, we have our post start, and and we have our warm-up enrichment. Let's just break this down real quick of what these mean in terms of getting the engine to fire off and run at a pretty stable air fuel. So we have our pre-crank prime that's adding a huge pulse of fuel whenever we're going and turning on the ignition key. In this case, we're setting it into a key on status. So we turn the key on, the injectors actually will squirt in a batch fire. They're going to be squirting what we specify here in the pre-crank prime table. This gets the engine primed up with a little bit of fuel for it to fire off a little bit easier. This does aid in starting. Now, it's going to transition from the pre-crank prime to a cranking enrichment table here. We're going to find that it sources the coolant temp that we're at, and it looks at this multiplier, this multiplication factor. This is going to multiply wherever we're at in our main VE table. It's going to multiply under cranking conditions. Now, if we switch here to fuel, we're going to find that we're at 0 MGP at 0 RPM. Right now, we're estimating here 66% cylinder filling. It's going to figure out what a air mass estimation. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.